Dear students, this is our third example, example 1.3 from the textbook, and this the textbook that I have also uploaded on the Blackboard, Principles of Electric Machines and Power Electronics by Sen. So in this example, it is showing that we have a magnetic circuit, and the relative permeability of ferromagnetic material they have given, that is mu r equals to 1200. It is neglecting fringing, so we have the air gap, but we are neglecting the fringing and the leakage. All dimensions are given in centimeters, and the magnetic material has a square cross-sectional area. So by meaning square cross-sectional area, you can assume that this is the core. So if this length is 2 centimeter, then this length is also 2 centimeter, and the area of cross section will be 4 centimeters square, or that will be equals to if you multiply it with 10 raised to power minus 4, it will give us in millimeter squares, minus 4. Then we have determine the air gap flux density. So this is the air gap. So first of all, it is asking calculate the flux that will be flowing through this air gap, and the density of the flux, that is B, and the magnetic field intensity, that is H, in the air gap. These three quantities are required. So if you can calculate flux and flux density, the rest of it will come very easily. There are no issues, because we know that after calculating the flux, here you can easily calculate this will be area of core, because there is no fringing effect. And if you want to calculate the magnetic field intensity, this will be very simple, B divided by mu, which is actually equals to mu naught into mu r. Mu r is given. So the main thing that we need to calculate is the flux. Now this is what the circuit is given. Now let's make equivalent magnetic circuit out of the given core and its condition. So we can see that we have two sources, and by applying the right hand rule, our fingers will curl in the direction of current in the coil, and our thumb will point towards the direction of magnetic flux. So if you can see, this is the fingers will curl, and where is the direction of our thumb? It is upwards. It is the direction of the flux that will be produced in this coil will be upwards. Let's look at the second coil. Here also, if we see, where is the direction of the current? Here it is like this, and this. So if my right hand's fingers will curl on the direction of the current flowing in the coil, again my thumb will point, and the flux direction will be this one. So I call this flux 1, and I call it flux 2. So the equivalent magnetic circuit will have two sources. We will have two sources, and this is F1, which is producing a flux 1, and then we will have another source also, which is also producing flux in this direction, that is called flux 2. Now let's look at the core in itself. So when we look at the core, and here I will select it from here, from where I have done this, from this to this area, there is one flux that is flowing. For example, from here up to this point, there will be flux 1, and after this point there is a node at B, the flux can be divided. So there will be one resistance that will represent this area which I have marked in green, and we can call this reluctance of the core as BAFE. This is how the book is using it. So B point from B to A to F to E, BAFE. Similarly, when we look at the source F2, from there also we have a reluctance of the coil, and I'll change the color and I'll show you with maybe this from here to here to here. So here again we will have B, C, D, B, C, D, E. This is another flux for this coil. Okay, this is reluctance B, C, D, E. And after, from this point, now from this point, this I will be showing with the, you can say, okay, red color. From B to E, number one, we have a core. So we have the core from B to E, we can call it RBE. And then we also have the air gap, I can call RG. So this is how actually I have modeled the core into a magnetic circuit. So how do I know which to which? Because you can see the flux 1 and flux 2 from RBAFE, this green circle is one reluctance. There's one flux is flowing through this area. BCDE, the blue one, the BCDE, there is one flux flowing through them, and in the center branch there is a division or addition of the flux. So now what will happen is, overall now we can see that flux 1 will be flowing through this, flux 2 will be flowing through. This is a typical electrical circuits problem. And here in the center branch, what will be the flux? It will be flux 1 plus flux 2. So I hope you guys have studied your electrical circuits correctly. If you guys have studied your electrical circuits correctly, then this should not be a problem. And if you guys did not study it hard, then it might look confusing, but it is not that confusing. So from this circuit, we can make two equations. If we apply the KVL, we have two loops here in the circuit. What are the? This is the loop number 1, and this is the loop number 2. So if we apply, and this is similar to this, so F1 will be equals to, if we consider loop 1, L1, and this is L2. For L1, loop 1, F1 equals to flux 1 RBAFE, the drop across this one. And then when we go into the branch, what will be the drop across this branch? The drop across this branch will be the current flux 1 plus flux 2, and the drop across this one and drop across this one. So this will be RBC, RBE, and the next one will be flux 1 plus flux 2, that is into R of G. So we can write the equation for loop 1. This equation will become F1. If we open the bracket and combine the similar, look, this is this multiplied by this, and this multiplied by this. So we can easily write this flux 1 equals to RBAFE plus RBE, this and this RBE plus RG, and we combine by flux 2 RBE plus RG this. This is our equation number 1. And the second equation for loop 2 in a similar fashion like what we have done here, we can calculate F2, flux 2, that is flux 2 into RBCDE, flux 2 into RBCDE. Then we will add again this drop against this and this. So L2 is this loop. We have flux 1, flux 2, RBE plus flux 1, flux 2, R of G. So we will calculate F2 is now equals to, I call this equation 1. F2 will become equals to flux 1 RBE plus RG, and the other one will become flux 2 RBCDE plus RBE plus RG. So these are now two equations. If this is F of 2, now we have two equations. This is called now 2. What are the variables? Variables, if we are able to calculate all the reluctances, then flux 1 and flux 2 are the two variables, because if we know the values of F1 and F2 also, we can easily calculate the values of, we have two equations, we have two variables, we can calculate the value of our flux 1 and flux 2, phi 1 and phi 2. And in the circuit we can see, in our circuit also we can see both the fluxes add here, and from the air gap the flux that will be going will be actually equals to total flux, flux 1 plus flux 2. So that is the whole question. So let's see for our equation 1 and 2 what are the values that we can calculate from our given data. So the first thing will be, let's see, can we calculate F1? Yes, we can calculate. Let's change the color and let's make it red. So can we calculate F1? Yes, F1 equals to N1 and I1, and this will become 500 into 10 ampere. So what will happen? We have the value 5000 ampere turns. So we have F1. Can we calculate F2? Yes, N2, I2, we have N2, it's 500 amperes. What about the current I2? Do we have the current? Let's see. They have not written it. But what do you think? What should be the current? Let's see, let's make it little clean and just look at the diagram. Oh. So I was cleaning this. Okay. And let's see, they have given us only one current, and what should I do? So look at this one current is entering this coil from this point A, and from which point this current is leaving the coil? Can you see? It will go to point B, then the same current goes to C, and the same current goes to D, and then the circuit gets completed. Maybe it is connected to a battery. This is positive terminal of battery, this is negative terminal of battery. So the same amount of current is actually leaving the coil also. This is the same coil, and that's the magic of electromagnetism. So how we have 10 ampere and 10 ampere? So again we have 10 equals to 5000 ampere turns. So we have, for these two equations, we have calculated F1 and F2. Now let's look at the reluctances. One of the first reluctance that we have, that we need to calculate, RBAFE, that is from point B, A, F and E. So how can we calculate this? R equals to BAFE. We know the formula, length BFE and we have mu r, mu naught. Have they given us the relative permeability? Yes, into area of the core. So let's look at the current. Let's look at the length, mean path length. What will be the mean path length? So if you calculate the mean path length, this length will be, and this you have to look into these dimensions, and I hope you guys can easily calculate it. So the length will become basically, so the squarish core from this point to this point, the length is actually, you should calculate, but I will tell you 52, this length, and everybody should be able to ensure why it is 52. This is also 52, and this length is also 52, and this is in centimeters, and so there should be no mistake. So what we will do is 3 into 52, because there are the three sides, and it is in centimeters, so we have to convert this into meters, divided by mu r. We know it is 1200, and mu naught is 4 pi into 10 raised to power minus 7. And the area of the core that I have calculated, actually it is, they have given just 2, but they have said it is square, so the area will be 4 into 10 raised to power minus 4. So the value, if you calculate, and you should be able to calculate this very carefully, this will become 2.58 into 10 raised to power 6 ampere turns per Weber. That is the unit of reluctance. So we have calculated RBAFE. Now if we look this, so what have we calculated? For our equations 1 and 2, we have calculated RBAFE. Yes. Okay. Now from the diagram we can see that RBAFE, if I clean this, the impedance from this one and the impedance that I am marking in green now, they both are actually same. They have the same dimensions, the same core material, and everything is same. So we can write that R, so the second is, and we named it as RBCDE. RBCD is equals to actually RBAFE. So now for the equation 2, we know this. Now what we need to calculate, we have to calculate RBE and RG. So can we calculate RBE? Yes, we can calculate. That will be hopefully not that difficult. So RBE is equals to length from BE to E, mu r, mu naught, area of core. What is the length from LBE? That will be actually 51.5. Yes, from here to here we have 52, and we will subtract, if we will subtract this one from here, the air gap, it will become 51.5 centimeter. So this is actually 51.5 into 10 raised to power minus 2, and then we know mu r is equal to 1200, mu naught equals to 4 pi into 10 raised to power minus 7, and the area of cross section is 4 into 10 raised to power minus 4. So the value will become RBE is equals to, that is 0.82 into 10 raised to power 6 ampere turns per meter. So we have this equation also, we had this equation also. So in our equations we have calculated RBE, and this is actually RBE, and here we have also calculated RBE. Now only thing that is remaining is RG. RG is the so RG is the air gap. So the length of air gap we know, LG mu naught into mu r into, so the length of air gap is, we know, 0.5. 0.5 into 10 raised to power minus 2 divided by, again, 1200, 4 pi into 10 raised to power 10 minus 7, 4 into 10 raised to power minus 4. So the air gap will be, and we can see how much larger is this reluctance value as compared to the core elements, because it is the air gap and it's an unfriendly atmosphere. So here we have calculated these values. So now if you put them in all these values, now we have calculated Rg also. So sorry, this so equation 1 and equation 2, we have calculated all the parameters except phi 1 and phi 2. So if you put all these values that you can do, so eventually the value of the values that you will get, and you can solve this equation. So this is a simple the solution for mathematics. You can solve this, and eventually you will get two equations, and from those equations you can easily calculate alpha 1 equals to alpha 2 and the value of alpha 1 and alpha 2. I'm skipping that part because it is basic mathematics and the video is getting larger, and I hope all the guys are listening. So the total flux that I told you before, the total flux that is passing through the air gap is actually equals to flux 1 and flux 2. So the flux through the air gap is flux 1 plus flux 2, and that is actually equals to 4.134 into 10 raised to power minus 4 Webers. This will be the total flux. Now if you have the flux, this is the answer for, that was the first thing that was required. The second thing that was required was flux density. So if you have the flux and you have the area of air gap, it has no fringing. So we have star minus 4 divided by the area was 4. So this will become flux density 4 into 10 raised to power minus 4. So the flux density will become 1.034 Tesla. And the last part was to calculate the, this is magnetic flux density through here. The last part was to calculate the magnetic flux intensity. And here we have 8G. What is this mu? This is actually mu naught because it is the air gap. So 8G will be B of G over mu naught. That is equals to 1.034 divided by 4.2 raised to 10 raised to 7. So 8G will become 0.822 into 10 raised to power 6 patterns per meter. So this is how we have calculated all the three values. Okay students, thank you.